example of a genetic variation that influences vulnerability to depression. So is the Val allele a new mutation that needs to be eliminated? No, I'm afraid not. If you note, that Val allele is quite a lot more common than the met allele. And the Val allele is universal in our primate ancestors. It's the met allele that turns out to be new, and it appears likely that it's gradually spreading, perhaps because it reduces vulnerability to bipolar disease and depression. More lives have been saved by public health and hygiene than by all of medicine put together, but like everything else, there are side effects. Lack of exposure to pathogens, especially to worms, deprives the immune system of certain inhibitory components. Work by Graham Brooke describes how type 1 diabetes, Crohn's disease, and asthma are all more common in children who are raised in pristinely clean environments. And Mel Reeves, who's written a wonderful book about evolution and cancer, notes that even acute lymphoblastic leukemia is quite a lot more common in children who are raised without exposure to aromatic pathogens. Dirt kills you, but on the other hand, exposure to a certain amount of dirt and infection seems to be the normal environment for our bodies. If we don't get enough of it, something is likely to go wrong. Douglas Wallace, a well-known geneticist, took a group of scientists to a meeting in Cold Spring Harbor some years ago to look at the evolutionary forces that were shaping certain genes, using sophisticated techniques to look for the signals of selection acting on certain genes. ADAH, lactase, DRD4, I won't go into the details here. It's important to recognize that new strategies in combination with genome data allow us to hone in on a particular locus to identify whether it's been subject to recent, strong, positive selection. The kinds of selection forces operating may be different in different environments. For instance, for people who are living in equatorial areas, heat is a constant problem, and salt balance has to be maintained at all costs. For people living in northern climates, keeping cool isn't much of a problem. Salt is often in more plentiful supply. And so natural selection seems to have shaped differences that change the vulnerability to hypertension. In work just reported by Young and colleagues, a particular locus, GMB3-825T, turns out to influence systolic blood pressure quite dramatically once you adjust for latitude. This gene has a strong latitudinal climb and may be responsible for why certain populations are more vulnerable to blood pressure in certain environments than others. The second reason why bodies are vulnerable to disease is because of competition with other organisms that evolve faster than we can, much faster. An E. coli can have a new generation in just a few hours, and of course for us it takes something more like 20 years. It isn't just pathogens. Predators and conspecifics, that's things like wolves, bears, and other humans, are also evolving quickly, and arms races can develop. But the big problem here is bacteria and viruses. Implication? Infection mediates all kinds of effects shaped by natural selection, not just the infection itself. Selection for a gene that prevents infection may make us more vulnerable to something else. You might think that after coexistence of the streptococcus bacteria with humans for millions of years, that we get used to each other. And I'm afraid no such thing has happened. What really has happened is that the defenses and counter-defenses have just gotten more sophisticated as the millions of years have rolled on. In particular, the streptococcal bacteria has antigens such that they're so similar to our own that when we make antibodies, we're liable to damage our own tissues. Like, for instance, with rheumatic fever causing damage to the joints and to the heart valves, scarlet fever causing damage to the skin, and obsessive compulsive disorder, or psychiatric illness, because of damage to a certain area of the brain. Third reason why natural selection can't make us more vulnerable to disease is because no trait can be perfect. Every single one is a trade-off. Many people have heard about the example of sickle cell anemia. It's a very specialized case, but it's still worth going into. The distribution of sickle cell trait in Africa almost exactly mirrors the distribution of malaria, leading a number of people to speculate in the middle of the 20th century that somehow the sickle cell trait might protect against malaria. The proper studies were done to test this hypothesis, and indeed, individuals who had one sickle cell gene and one other hemoglobin gene were less likely to get malaria than those who had two non-sickle cell genes. Of course, those people who had two sickle cell genes were likely to get very sick and die young. Now things get more interesting, however. In a paper by David Weatherall and colleagues, alpha plus thalassemia, they again found a concordance between the distribution of malaria in Melanesia and the distribution of the gene. Did this gene protect against malaria? No, quite the opposite. It made individuals more vulnerable to malaria. They hypothesized that it's conceivable that individuals with alpha plus thalassemia get the mild form of malaria, Plasmodium vivax, early in life, which provides some protection against the life-threatening form of malaria, Plasmodium falciparum, later in life. Exactly how to get a firm test on this is not clear, but it's a wonderful idea. It illustrates how natural selection can sometimes shape genes that make us more vulnerable to disease. This area of research has flowered, and numerous studies now confirm the protective effect, apparently not just against malaria, but against some other infectious diseases as well. Gout is something that you would think natural selection would have done away with long ago. Gout is nothing more or less than the deposition of crystals of uric acid, like grains of sand, in the joint. That's what it feels like too, extremely painful. So why didn't natural selection lower the uric acid levels for our entire species so that crystals didn't get deposited in our joints? Well, it turns out that this is a good opportunity to look at comparative data. It turns out that the levels of uric acid are very directly correlated with the lifespan of different species. It also turns out that uric acid is quite a fine antioxidant. It looks likely here that natural selection has increased levels of uric acid to protect against aging in those species that have a long lifespan. And that in those with a very long lifespan, namely humans, there are some individuals unlucky enough to have levels that give them gout. The rest of us just benefit by living longer lives. Of course, like everything else, it's a bit more complicated than this, and that there are further substances that inhibit crystal formation. Nonetheless, the general argument still makes sense. Bilirubin is another good example. Bilirubin is the chemical that accumulates in people whose livers have failed, causing jaundice and eventually death. So bilirubin, of course, is a byproduct of hemoglobin breakdown, and a certain proportion of blood cells die every day and are swept from the circulation, and the bilirubin is a result. But if you think about it more carefully and look at the biochemistry, you realize that bilirubin is not in fact necessary. One of the metabolic pathways from heme to bilirubin is biliverdin, and biliverdin is water soluble and could quite easily be swept out of the body with water in the kidneys. So why isn't it? Why use energy to make a toxic substance like bilirubin? Well, it turns out that bilirubin is an extraordinarily effective scavenger of lipophilic reactive oxygen species. It looks like bilirubin levels are shaped in order to protect us against these damaging radicals. Implication? Many apparently harmful traits, such as the very existence of bilirubin in our body, turn out to be useful once we look more carefully. The fourth explanation is constraints on what natural selection can do, and it has quite serious constraints. This was the old idea that was used to explain almost every reason why the body wasn't better, but it certainly is powerful in any case. First is path dependence. The body can't ever start fresh, because the intervening models might not work as well. An eyeball that's half-turned right side out wouldn't be a good idea at all. It's exactly the same reason that our computer keyboards are laid out in ways that make us type more slowly. It was originally designed to prevent the keys of typewriters from sticking. Now it just slows us down. You're welcome to use a different kind of keyboard if you like, but I'm certainly not going to. The retraining would just be too difficult, and the consistency with other keyboards in my life would make it impossible. Then there's mutation. The DNA code is not invulnerable to corruption. It's remarkably good, but it's not invulnerable. And of course, selection itself just isn't strong enough sometimes to do things that would be beneficial. Whether it's keeping a gene that's useful or eliminating a gene that's deleterious, happenstance is a really big factor. The role of chance factors in evolutionary trajectories is profound. If certain precursors to whales, something like hippopotami, had never gone for a swim, there would be no whales, or perhaps they would have emerged from some whole different lineage. Chance is profoundly important in the directions of natural selection. But this doesn't mean that natural selection can't shape things that are amazingly exquisite. For instance, what's the reason for our eyes being inside out? They certainly are inside out. The vessels and nerves run between the light and the receptors, and they exit the eyeball in the back, making a blind spot. As a result, the eyeball